welcome to another month and another Let's CTF video. This month, we're going to be doing something a little bit different. Rather than taking a look at a CTF challenge and kind of walking through how to solve it, we're going to talk about a particular type of vulnerability, explain how it works, and then exercise some code that's really going to show that off. So today we're going to be talking about stack buffer overflows. Without any further ado, let's go ahead and jump into our virtual machine over here, where we have Visual Studio already open. Now, this Visual Studio project is intended to be something we can use to illustrate these stack buffer overflows. Okay. Here in the main function, all we're doing is calling another function inside of a structured exception handling block. This is these underscore try underscore except things. If an exception was to be generated, then it would call this filter function, and the filter function would determine what to do next. In this case, even if we do run the code that's guarded by it, it does nothing because the critical code that I care about there is actually inside of that function. Looking up at that filter function itself, we can see that all it does is print out a flag and then return that the exception has been handled, and to go ahead and execute what's inside of that block there. Again, that block just has do nothing in it. In this test func, the function being called, we see that we have some structure here called check overflow, and we're initializing that to all zeros. Then we're setting the canary element of it that we see here. That canary element is going to be set to 1, 2, 3, 4, 5, 6, 7, 8. That's just a predictable value. It's something that we can check for after doing something else. Because what we want to occur here is that if somebody was to overwrite beyond the end of that input into that canary, we want to be able to detect it. Now, because this is a local variable, it's going to be declared just inside of the scope of this function. That means it's going to be put on the stack. That's different than global variables, which sit in a data or R data section of the executable. And that's different than something that was created using, for example, malloc, which would be then in the heap. So this is a variable that exists on our stack. And we'll see that in a minute and what that looks like. In order to kind of go further, let's go ahead and take a look at what a stack looks like for a program like this. And this is going to be the case on Intel systems and any system that has a stack-based virtual machine or a stack-based machine inside of it. So what we have to begin with is we have the C runtime that kind of starts everything up, and then it calls into main. So the CRT is going to call main, and then we saw that main is going to call this test function. So CRT calls main, main calls test func does some stuff, and then is intended to return back to main, which will then return into our C runtime and eventually terminate the program. Each of these calls is using the call instruction. We have a call instruction in Intel assembly. You tell it what to call, for example, call main, and it redirects execution there. And then we have some instruction after that call. When we make the call, it's going to take the address of the next instruction and push that onto our stack, because we need to know where we're going back to. This is part of how this stack-based system works. We also have some arguments to main. We have our argv and we have our argc. Those are arguments that are passed to main. And in order for main to get them, they need to be put somewhere. Different calling conventions put this different places. We're going to be looking at a 32-bit program here, and the 32-bit program is calling main as a cdecl function. That's just the name of the calling convention being used. And that means that these are going to be put onto the stack using the push instruction. And in fact, these are actually out of order because they're normally pushed in the reverse order of the function arguments, but that's okay. That's not going to be crucial to the demo that we're doing here. So when the C runtime calls main, it's going to push these. Main then might, inside of it, create space for local variables if we have them. So this is still the code in the C runtime. So let's take a look at what main looks like over here. The first thing it's going to do is, if we're using one, set up a base pointer, that is, uses the EBP register to point to our stack, so we don't have to keep moving it around when we make room for locals or push things like that. So it's going to push EBP, it's going to move into EBP, the current stack, and then it's going to make room for locals. Again, this is going to be done on the stack. All of this is stack-based when we're talking about the way that functions are called. So it's going to do something like sub ESP size of locals. Let me put a space there. Okay. Then it will do all of the other things that it's intending to do, including call testfunc. Now, if testfunc was taking arguments, it would push those first. So we'd see a push here, and then it has something that it's doing after that, so some instruction. Again, when we do this call, we're going to push the address of the next instruction onto the stack. So let's take a look at what our stack is going to look like, right? First, let's establish where our memory is. Stacks grow from high memory to low memory. They move towards 0. So I'm going to label up here as 0, and I'm going to label down here as the highest possible address in a 32-bit program, which is FFFF. Somewhere between these two values, we have things that were used by the C runtime. And then the C runtime pushed these arguments onto the stack. So these are the arguments for main. We have argv and argc pushed onto the stack, and then we have a return pointer. The address of this instruction here, let me label that green, this address is going to be put here. So that after main finishes, we can look at that spot on our stack and know that that's where we're going back to. Then we have any local variables for main. Anything that it does here, making room for locals, that's going there. Okay. Then we're making a call to testfunc. If we had arguments to testfunc, we would push them, and they would go on the stack here. There aren't any, so we just have the address of the instruction after that. We have some instruction. So that is going to go here. That is, again, it's another return pointer, but the purpose of it is when the next call we're making, testfunc, finishes, this tells us where to go back to. So we have the stuff from the C runtime, anything it was doing with its variables, anything like that, and then the arguments that are pushed for main, then the return pointer to go back to after main is finished, there in green. Then we have the locals for main. We're making then a call to our testfunc. Testfunc itself has local variables. So inside of testfunc, it's going to do that same stuff. Push EBP, move EBP ESP, and then it's going to sub ESP size of its own locals. So we also have space here for any local variables for testfunc. And we know that it has some, right? We know that it has that structure we created, and that structure had 5 characters, and it had space for our canary. Our canary is an integer, so that's 4 bytes large. We would think our structure then is going to be 9 bytes. But that's not actually going to be the case. Because this is not an even multiple of our address size, our word size, the C runtime is actually going to put some padding in between. So because this is not an even multiple, we're going to have 3 bytes of padding here. So we'll have those 5 bytes of our character array, 3 bytes of padding, and then that canary, making a total of 12 bytes. So just some vocabulary here. These things that are the locals for main, or the return pointer and arguments for main, we call that a single stack frame. That is the main function's stack frame. Same way up here, we have the locals for our testfunc and its return pointer, and if we had arguments, those are the stack frame for that function. We put those stack frames on top of each other, and that allows us to see where we've come when we need to come back at the end. So at the end of testfunc down here, eventually there's going to be a ret instruction, and that ret instruction is going to take whatever is on the stack and put that into the instruction pointer. That's how we know where to go back to. And if everything has been correct, that will return us back to this instruction here. But if we've somehow overwritten this value, for example, if our array here overwrites this canary and keeps going, we'll also see that we've overwritten all of our locals and potentially this return pointer. This is how things like return-oriented programming, or ROP, get their start. We would write a value here that is some other code, a pointer to a valid section of memory that is executable, that does something useful to us as attackers. Now, return-oriented programming is going to be an exercise for another day. I'm not going to go into that in too much detail, but we are going to see some of these overwrites in action. So now that we've talked about the stack, what it looks like, a little bit about stack overflows and these stack frames, let's take a look at what this is doing in practice, okay? Now, I mentioned that I have this try except here, this SEH block, and whether or not this comes in handy will depend on the environment we're in. We'll see that play out as we go forward. One thing to note is that we are doing a debug build, and we're in 32-bit. Now, we're in 32-bit just because I want to demonstrate argument passing on the stack and some of those things. Stack overflows can absolutely still occur in 64-bit. And that idea of having return-oriented programming or the return value on the stack, that's still true because the call instruction still puts it there. The only difference, sorry for the squeaky chair, the only difference is whether we're passing our arguments on the stack or not. And I'm enforcing a calling convention in 32-bit that does. So we're going to call testfunc, but with no arguments. Testfunc is going to make space for this local variable. It's going to initialize it to 0. It's going to set the canary part of it to 1, 2, 3, 4, 5, 6, 7, 8, do a scanf, check to see if that has changed, and if it has changed, print out the flag. If it has not changed, we do not print out that flag. Then it's calling exit with 0. I'll get into why I have that exit call there in a minute, but we should see that the function the program terminates after that with an exit code of 0 if we're able to get to that line successfully. Okay. This filter function, this is going to come into play later, so let's ignore it for now. And let's go ahead and execute our program. Now I'm going to uncomment this debug break. What debug break does is it throws a specific type of exception called a debug break exception. The instruction in assembly for that is int3. That will cause our debugger, if we have one, to automatically attach. Now, I have set up this system to use a just-in-time debugger. That means that if something throws an exception, then that debugger will be opened and attached to the process. I have that set up to use WinDebug. If you don't have that, you have the option of using the Visual Studio debugger by running this through this button here or hitting F5. If you don't do that, if you run outside of the local Windows debugger and you cause some kind of exception, then whatever handles exceptions is going to execute. By default, that's something called Dr. Watson. That is the Windows Error Reporting Tool, or WER. That pops up the box that you've probably seen that says, an exception occurred, do you want to send information to Microsoft? That's not going to happen here because, like I said, I've replaced that with the WinDebug executable. So now I'm going to run this, and it's going to hit that debug break. That debug break is going to throw an exception. That exception is going to be caught by WinDebug. And so we see that has happened. WinDebug's popped open here, and if we look at our call stack down here in the bottom as it loads up, we can see that we're inside of this debug break function, and that we got there from main. And the debug break function is actually just throwing this int3 instruction that I mentioned. We want to get back to main, so I'm going to go ahead and step out of this debug break instruction, and because I have debug symbols, I built this with debug mode, and I have a .pdb, a portable debugging file, I can also see where I am inside of my C code over here. I'm going to go ahead and step over some of these instructions until I get to the call to testfunc. So I'm at this call instruction. We're about to enter that function that we were talking about, and so we should see that execution continues up here in this area. There we go, up here. So I'm going to go ahead and keep going. And this time I'm going to step into because I want to see the behavior inside of that function. And now I'm at the top of it. If I was to unassemble here, unassemble at EIP, we could see the instructions for this do include that push EBP, that move EBP ESP, and that sub ESP, the size of my locals that I mentioned earlier. Then it's making room for some other preserved registers. That's because they have to be the same when you exit. Let's go ahead and step a little bit. And so now we can see that we are going to be setting this entire thing to 0. If I unassemble at EIP again, we can see we have XOR EAX, that just makes EAX 0, and we're writing into this local variable that we have 4 bytes at a time as zeros. And notice that we're doing that 3 times. That's for those 5 bytes plus the 3 bytes of padding plus the 4 bytes for that canary value. Then we're going to write that canary in. So these instructions here represent this initialization to 0, followed by this value here being written into the canary. Excuse me. So I'm going to go ahead and keep stepping. And we're going to see now we have a call to scanf as one of the next things we're doing. I'm going to step over that call. That means that I am telling the debugger, keep running until scanf returns. Over here now, it's going to have me put in some values. Just as a kind of exercise here, I'm going to, in this memory window, point us to our stack. That way, after we, there we go, after we make that call, we should see some values change. And now I'm going to put in 5 A's. Okay. Oh, I just completely stepped out of the program. So let's run it again and we'll see that behavior. Sorry about that. Here we go. So we'll run it again. We'll stop at that scanf this time and we'll actually see the behavior. Again, I am going to point this memory window to our stack. I'm just going to tell it to look at things at ESP. That's our stack pointer. I'm going to continue until we get to that test func call. So here we are about to call test func. I'm going to step into that. We see that we are doing that initialization. And now we're about to call scanf. So let me step over that call. And we're going to be watching memory down here for anything that changes after I input these A's. So we can see that we wrote 4 A's into memory here. And we actually also wrote a null pointer, but because it was already 0, it's not being written, not being shown here. We also see here that we have our 1, 2, 3, 4, 5, 6, 7, 8, but it's in reverse order. And that's because we're on a little endian system. So if we view memory byte by byte, it's going to be in the reverse order we expect. But if we view it as 4 bytes at a time, the system knows that it's treating that as a D word, and so it swaps the endianness for us into something readable. So if I display as a D word that address, which looks like it is A0F700, we see 1, 2, 3, 4, 5, 6, 7, 8 as we would expect. But if I do the same thing and look at it a single byte at a time, we see 7, 8, 5, 6, 3, 4, 1, 2. This is something to be aware of if you're sending raw bytes to something, but you need something interpreted as an integer or something like that. And that's where things like the struct.pack function in Python can help you translate those endiannesses for you. So we've seen that we wrote in our A's and we did not modify our stack canary. And that means this if here will fail. It should not print anything out, but it should exit 0. If I hit continue, we see we've terminated our process here. I come over to my window, and if I close WinDebug, it will completely terminate and say, yes, we did in fact exit with code 0. And that code 0 means that we successfully ran this exit 0 here, because if we had returned, then we would have had a 1 as our exit code. Okay. Now let's go ahead and run the thing again, but this time I'm going to write too many A's. We're going to go beyond the end of that buffer. And that's because scanf as a function is not aware of the structure size. It's just going to go until it finds that null terminator on the string that it's doing input for. That is potentially dangerous, and that's why we sometimes consider that scanf in that form, as opposed to something like an SN scanf, to be dangerous. So once again, we're going to step out. We're going to go just to the point that we are going to be calling that test function. So we're now at that call to the test function. I'm going to step into it again. And this time, we're going to write too many A's. So I'm going to go ahead and once again step over that scanf, but let me point at RSP again. Sorry, ESP, 32-bit. So looking at our memory, this is our memory around our stack pointer. Our stack pointer is CFF6B4, CFF6B B4. So our stack pointer is in here. We have these zeros that we can see from initializing those values. Let's go ahead and step over this scanf call again. But rather than fewer A's, I'm going to put more of them. And we saw that it created 12 bytes of space. So I'm going to put in, let me actually count, 1, 2, 3, 4, 5, 6, 7, 8, 9 A's. Hit enter. And we can see here that it actually wrote 9 A's, these 4141, 4141, 4141, 4141, and then that null terminator, right? So we actually wrote one more byte than that. And we can see that we also have overwritten these 2 bytes from our canary. We have 1, 2, 3, 4, but our 5, 6, 7, 8 got overwritten by this overflow. We wrote too much data. And that means when we do this comparison is going to fail. So we go ahead and we step, and now it's calling printf. We go back and we see that it has printed out that flag because we overflowed into that next value. Okay. Then it's going to call exit 0. And so we'll see that we exited with a code 0, but we printed our flag. So even though we never directly modified in our C code the value of that canary, it still did get modified, and that print happened. This is the basis of a overflow on the stack. This could also be an overflow on the heap in this case, because it would just be within that same variable space. So let's go one step further. Let's not just overwrite this canary, but let's also overwrite that return pointer that we saw. And I'm also going to remove this exit 0 so that we can witness the behavior that happens when we do that. Now, I mentioned stack canaries earlier, and we are going to be building with stack canaries enabled. If this all executed correctly, this function would return, we'd come back to main, and then we would return 1. So we would expect to see an exit code of 1 here. But if we run this, and I'm just going to hit go in my debugger, I'm not going to pause anywhere, but I am going to write significantly more A's than we have for that structure. So there's 12 for that structure. I'm going to write a whole bunch more than that. I don't really care how many, just a bunch. Okay, so we printed out that flag, but we can see over here that we are now inside of a function called fail with message, and that came from a stack failure. So we have overwritten that stack canary value, we have caused an exception, and if I hit go, we now see that we are in report guard stack failure. Eventually, I let it go. It can't go any further because that has exited the program. And so if I close, we see that our exit code is actually this very large negative number. And that's because it's treating it as a negative number. It's actually not. It's actually an unsigned number that represents the guard stack failure exception code. So we can see that we got the print inside of this block here, but that we didn't do anything with this puts. We only saw 1 print. We didn't see 2. And if I was to comment this out, that would be even more obvious. In the process, I'm also going to comment out our debug break here just so that we don't have our debugger pop up. Let's run this again. First we build it, then we run it. Once again, I'm going to give it a larger input than it has local variables for to see that guard stack occur. And in fact, we see that. If I ignore the error, then we're going to see that pop up in WinDebug because now we have that guard stack exception. Note that we did not open for that debug break because we commented it out. It's not there anymore. But this is trying to break into something that has had that debug exception happen. One thing to note here is that we don't have any prints, right? We didn't get that print because we commented it out. If I just close WinDebug, it'll allow this to continue executing, and we can see once again, we have that same number as our terminator. Notably, despite the fact that we do have an exception handler here, it should call the filter function, that is not done for this stack canary or the stack cookie exception, because a stack cookie exception calls a fast fail and terminates in a way that can't be caught. If we do want to be able to catch that, we have a couple of options. If we, as our CTF designer, wanted to keep this exact behavior, we could have this application called by another one that checks that exit code and says, do we have the stack cookie exception exit code? Another option is to disable stack cookies so that that exception can never be thrown, and instead this filter exception inside of our structured exception handler can execute instead. So let's try that. I'm going to come in here just into our project properties, and I'm going to turn off the GS flag. So when we compile it, we're telling it do not compile this with stack cookies. So it's now disabled. Click OK. Build this again. Now when we run it, we'll see different behavior because, yes, we're going to overwrite where that stack cookie was, overwrite where that return pointer was, but now when an exception is thrown, it's able to check that SCH record, see, okay, we have a structured exception handler here, and kind of know that it's able to go from there. Now, we do still get this runtime warning, and that's just an element of the CRT because we're calling, returning to an invalid pointer. But again, I'm going to hit ignore on this, and this time we can see that we exited with a code of 1, and we did print out a flag. And that's because the structured exception handler caught this. It said, call this filter function. The filter function said, okay, print this out and return this value that says we have handled this exception. Go back to the exception handler block, which would have been this do nothing block here, and then continue down from there. Don't go back to wherever the exception happened. Instead, go to main. Then we hit this return one function, and that set our exit code. So by setting the structured exception handler and specifically disabling those stack cookies, we are able to see this other behavior that we had. So this entire application is intended strictly to detect and print something when some kind of overflow happens. When it is an overflow of locals and I uncomment this here, then we see that print. If it's an overflow beyond that return pointer that would have gone back to main, and we don't have stack cookies, then we're going to call this function for our exception handler. We have a print there. If we do have stack cookies enabled, we saw that this code still executes, but as soon as testfunc tries to return, it throws that stack check failure, and it never goes back to main, and it doesn't go to our exception handler. So you've now learned a whole bunch about the behavior of C programs. You've learned about how the stack looks, how the stack behaves, and how a stack buffer overflow occurs in C, and what it kind of looks like when we are trying to exploit it. In the future, we'll talk a little bit more about return-oriented programming, putting a value there in that return pointer that is useful to us as attackers, and also some other attack primitives, some other things around exploitation, and of course, we'll go back to solving CTF challenges as well. But I thought having a break from that to really talk about some of these specific exploitation elements and these specific vulnerabilities might be nice to see. Thank you all for watching me for the last half hour, and I hope that you have a wonderful rest of your day. We'll have another one of these videos next month.